Thank you for coming. Tonight is also very special since we decided to launch the evening public lecture series of TBAE. I hope it will continue in future as well. Our first speaker today is young scientist from MIT, Tansu Daylan. Tansu Daylan has kindly agreed to help me in organizing this conference. He's also a speaker at the conference today and tomorrow. And thank you for this, and we are very proud of him. And he is a bright example for all of you as well. Tansu Daylan graduated from Robert College and then went to METO, Middle East Technical University, where he did a double major in electrical and electronics engineering and in physics. Then he went to United States and obtained his PhD in physics from Harvard University. He mainly works on various statistical methods, signal processing, neural networks, transdimensional Bayesian interference as applied to problems in astrophysics such as cataloging, detection, and characterizing of dark matter and exoplanets. A young physicist and pilot, Tansu Daylan, I can say, from the blue sky went to dark universe exploring dark matter in the universe and exoplanets. Today he will give a public talk titled as Detecting and Characterizing Exoplanet with the Transiting Exoplanet Survey Satellite, TESS, NASA's new exoplanet hunter. Thank you very much. Please join me to welcome warmly dear Tansu Daylan.
Thanks. Okay. Thank you very much for the nice introduction and also for the invitation. So I think this is all set there. I don't need to connect it, but if you can't hear me, please let me know. All right, so today's agenda, as you can see, is to talk about exoplanets and a NASA experiment called the Tess, Transiting Exoplanet Survey Satellite. But I gave a similar talk a couple of weeks ago in Sabancı, and I know a large fraction of the crowd actually has already listened to it. So I will try to keep some of you awake by making jokes, but I hope I don't get you sleep. But let's make this as interactive as possible, so the contents shuffle around. Please feel free to... Okay, so let's get started. So this is the outline. The first part, I'll talk about essentially the idea of exoplanet, what an exoplanet is, and try to just introduce the idea of looking for planets outside the solar system. And then I will introduce the Transiting Exoplanet Survey Satellite. At the very end of the talk, I will talk about discovering and characterizing exoplanets using this machine and in general, and probably just finish off with, because this is a public talk, I will try to finish off with some discussion of extraterrestrial intelligence and the Fermi paradox. All right, so, but just for those of you who don't know me, real quick, in one slide I'll explain what I do and what I think about mostly. So during my PhD, I spend most of my time thinking about dark matter, and that's what I will be discussing during my lectures tomorrow and the day after that. There will be 4 of them, and they'll just walk you through the whole idea that I presented in my PhD thesis. But today I'm not here to talk about dark matter. About a year ago, I joined the Tess team, And as a postdoc, I've been working on Tess to discover exoplanets in the Tess data, which will be the subject of today's talk. One common denominator of these two is the fact that both dark matter, as its name implies, and also exoplanets are dark. Dark matter is dark just because we don't understand it. It's not dark because it's actually black. And for exoplanets, especially those that transit, they transit in front of their stars and they dim the star for a certain time, and that's why they're black in some sense. Now, another common denominator of these three is actually statistics, because when you try to understand physical phenomena, you have to do statistics and you have to do it right. Otherwise, you don't get anywhere, or actually use the data to arrive at the wrong conclusion. An unfortunate result of actually doing statistics is you get to code and code and code and just fix bugs. So that's what we actually do. All right, so here we go with the exoplanets. Now, you know that there are 8 planets in our solar system. Just starting with this very bare fact, it is, I think, a very natural assumption to just assume that there must be exoplanets outside the solar system as well. And obviously, just before 30 years ago, we did not have observational evidence to support this statement that I just made. It was essentially just like this broad idea that there must be exoplanets or planets outside the solar system, just like ours, just like we have these 8 guys. However, in the last 30 years or so, we actually obtained observational evidence that there are such guys, and now we can even start counting them and make statistics and learn about their population behavior as well. So this is a giant leap for mankind in some sense. It actually all started with this guy's detection. It was essentially the first exoplanet to be discovered. It wasn't discovered around a usual star that you might think is the case, because most stars are just like our sun. However, so this very first detection was around a dead star, and there's actually a reason why that is the case. Dead stars essentially, or when I say dead star, I mean a pulsar. Pulsar is a rotating dead star or a neutron star that sends out electromagnetic waves with a certain period. Now, using this period, you can first start studying its the temporal variation of the period, and then if you see certain fluctuations in that period, then you can understand that there are actually 2 bodies or multiple bodies in that system, not just one. So using that observation, you can conclude that there must be exoplanets outside, in orbit around the pulsar. So this was the very first detection. And after that, there have been many. So far, we know about 4,000 exoplanets, and the number is increasing almost every day. Now, one thing I have to probably get across at the very beginning is that if you just take a telescope, a decent telescope, and just point it at a particular star with a certain exoplanet, let's assume that there is an exoplanet for sure, and hope to just get photons from the exoplanet, it is probably not going to work. The reason is typically stars are much brighter than exoplanets. And you might probably know the reason why stars are energy sources, so they're very bright, so they produce energy and radiate a lot of photons. Exoplanets don't. They only have thermal radiation because they have obviously some finite temperature. However, that temperature isn't high enough for them to send out that many photons. Usually, very typically, this is a ballpark number, stars are brighter than their exoplanets by a factor of about 1 billion. So that is really hard to actually achieve observationally. So what you hope to do is you go to the infrared region, where typically exoplanets, because they have a finite temperature, exoplanets are relatively brighter with respect to their stars. So you can, for certain cases, you can hope to actually get a glimpse of such exoplanets. So this is an example of such a detection. So you see these guys that orbit the star. In order to do this, people use coronagraphs that block out the light from this star. And that's the only way you can actually start resolving the light from these exoplanets. That's a very cool detection. But unfortunately, it's very rare. So it doesn't happen that often. So most of the time, you have to rely on indirect observation to actually detect them. And when I say indirect, I hope you don't start questioning it, because although it's indirect, it is actually much above 5 sigma. That is, we statistically confirm using independent methods that there is an exoplanet. So there are two such ways. One exploits essentially the temporal resolution, the fact that we can start and stop chronometers, like we actually can measure differences in timing, and I'll get to that. Second, we exploit the idea of energy resolution. That's called the radial velocity method, and the first one is called the transit method. I'll come to the details of these now. I'll start with the transit method. So in the transit method, you have a star and an exoplanet that orbits around it. Obviously, in order for this to work, the planet has to be orbiting the star at such an angle that it's in front of your line of sight. Otherwise, obviously, this doesn't work. And once it passes in front of the star, the luminosity of the star, or actually the flux that you get from the star, the luminosity doesn't change, but the flux that you get from the star temporarily decreases. And then if you start seeing this signature again and again and again with a certain time period, then you start saying, maybe there's an exoplanet in front of that star. So this is just a movie presenting the same idea. So there's a star, there's an exoplanet. So here there's the so-called light curve, the flux as a function of time. And now you see two such stars with two different exoplanets. The difference is one exoplanet actually has a larger radius, which means that the transit depth will be larger by the square of the radius, because it is proportional to the area of the exoplanet, or the area ratios. And that's the smaller guy. So that's how we can infer the existence of an exoplanet around the star, provided that it's in front of our line of sight. Now, the second method is called the radial velocity method, which I will spend minimal time on, because that is not how we detect exoplanets using Tess. In the radial velocity method, you again have a star and an exoplanet. If you don't have an exoplanet, this doesn't work for obvious reasons. Now, once you have a two-body problem, what you can try to infer is the relative, or actually, so the relative velocity of the sun with respect to the common center of mass of the system, because these, the star and the exoplanet essentially orbit a common center of mass. Despite the fact that the star is very heavy, it doesn't have infinite mass. So there's a common center of mass which is not the same as the center of mass of the sun or the star. So there's essentially a motion of the star with respect to that common center of mass. So the observational probe that allows this inference to be made is the Doppler shift, where if there's a line of sight motion of the sun, its emission lines or absorption lines essentially either move to the right or to the left. Either it becomes blue shifted or red shifted, depending on which sign the relative velocity it has. And using this, you can start to infer the existence of the exoplanet without even taking an image of the system. So far, I've only discussed systems in which you just see a star. You don't actually see or angularly resolve the exoplanet. That is very cool, because that's why we call it indirect observation. Now, if you only use one method, let's say the transit method, that is usually not enough. So what we do is we make sure that from the same system, we get both the radial velocity signal and also the transit signal, so we can make sure that there is an exoplanet around that star. Now, once you start detecting these, I think the very first question you ask is, what can I do with them, or why do I even care about exoplanets? Well, there are two main motivations. The first one is to understand the origin of the solar system, because we have evolved on an Earth, or on a planet, and we start asking the question like, there are these different planets, there's this planet below us. How did they even form? How did they even come into existence? By understanding exoplanets and at different stages of their, obviously, evolution, we can start understanding our own solar system. And second, if you even find the twin Earth, that is an exoplanet that looks very much like Earth, then we might even possibly find extraterrestrial life, or at least start understanding the conditions in which such extraterrestrial life starts to arise. So those are the two main points, or main motivations for us to think about this problem. Okay, so next I will talk about Transiting Exoplanet Survey Satellite, which is essentially a NASA experiment to do this using the first method, the transit method. So for the moment, just forget the radial velocity method that I just described and concentrate on the transit method. So this is Tess. And it's got 4 cameras, as you can see. It's got solar panels and a bunch of electronics that allows Tess, the machine, to send back, well, first record and then send back the data to Earth. It's also got an antenna, which is on the other side. It just rotated, so you can't see it. This is this is pre-launch, obviously. So you now actually see the antenna and 2 people just in the clean room doing the final touches on the instrument. Obviously, there are many tests that you have to do before you send something into space. It's very expensive to do those tests. So at the very end, Tess was launched into space April 2018. And that's essentially the Falcon 9 that sent Tess into space. It was launched by SpaceX from Kennedy Space Center. And this is a movie of 2 CCDs of Tess. So Tess, as I said, has 4 cameras, and each camera has 4 CCDs. So that ends up being 16 CCDs. A CCD, by the way, is a charge-coupled device. It's it's the device that allows your iPhones or smartphones to take pictures. It's the same CCD here. It's just much more sensitive. So space-based CCDs, or CCDs that are designed for space applications, have much lower readout noise, or dark current, what we refer to. So they can actually look at very black regions in the sky and still not be noise dominated. So Tess has such optical is such an optical telescope with such CCDs. So here you basically see an object moving, and there's also a tail. So this is a comet. And you also see some systematic effects due to the CCD itself. And the next image, will now show the 16 CCDs one by one. So you count them like this. So camera 1, 2, 3, and 4 with each CCD. So camera 4 is has been pointed for the first year at the southern ecliptic pole. And in the second year, so the nominal mission is for 2 years. In the second half of the mission, it will be pointed at the north ecliptic pole. So because this is the south, you may recognize what this is. If you're inclined to astronomy, it's the Large Magellanic Cloud. And this is the orbit of Tess. So that's Earth. And where's our moon? the moon doesn't show up, sorry. Okay, anyway, oh, here's the moon, okay. That's our guy. Okay, so that's Tess, so that's Earth. So Tess essentially is an orbital resonance with the moon in a 2-to-1 orbital resonance. This allows the orbit of Tess to be very stable. Otherwise, if you just put an object in between the Earth and the moon, its orbit becomes destabilized by the moon over very short time scales. So this 2-to-1 resonance allows Tess to make very stable measurements over tens of years, so to speak. And you don't actually care after tens of years because it will run out of fuel anyways. So as long as NASA has budget to sustain Tess in space, it is good to go. It looks so. And I've already mentioned that it's got 4 cameras, so now you'll see each camera one by one. So that's a 24 by 24 field of view. It's pretty large for space applications especially, and there are 4 of them. So at a given time, you actually get to observe a really large fraction of the sky, 24 degrees by 96 degrees at a given time. And you stare at this patch of the sky for about a month. And then you start rotating the cameras, and once there's actually a GIF about that, but so you start rotating the cameras until you cover pretty much the hemisphere, and then you turn to the other pole and then do the same. That's the idea about the survey. And I already mentioned that it's got 4 CCDs, so this is kind of a repetition. This is taken from the Tess office at MIT, just pre-launch, checking the CCDs. Okay, so this is what I was just referring to. It goes and surveys the southern hemisphere first, and then it rotates, does the northern hemisphere. So we will soon start the northern hemisphere in July. So we are about to be done with the southern hemisphere. So we'll continue with the north. And the nice thing about the northern hemisphere is that we will start staring at the Kepler field. So Kepler was the precursor to Tess. It had basically a much smaller field of view. So looking at the same patch of sky will be a very rich science, essentially, because we will be able to cross-check our results with Kepler and also discover more planets in the same region. So one more thing to define. So JWST is the James Webb Space Telescope, and it's got a synergy with Tess, if it ever launches, because it's basically, so Tess is designed to actually look at the JWST's continuous waving zone for a long time. And what this does is, if Tess, for example, detects some exoplanet in that region, JWST will be directly able to follow up in order to characterize the atmosphere, if it has any, the atmosphere of that exoplanet. So there is going to be a synergy between the two. And the level 1 science requirement of Tess is to discover 50 sub-Neptunes. The definition of a sub-Neptune is an exoplanet with a radius that is less than 4 times the radius of the Earth. That is just one definition that's useful. So that's the level 1 science requirement, and obviously measure at the very end also measure their masses. So this will give a catalog that will be very useful for further characterization. Now, the science potential of Tess obviously isn't just restricted to exoplanets. It can find, for example, all time variable objects in the sky, such as supernovae, comets, moving objects. So these are in our solar system. It also can look for optical counterparts to fast radio bursts or even gravitational waves. These days, we keep thinking about gravitational waves a lot, and that's one of the hot topics. If, for example, LIGO finds a signal, which it started finding regularly anyways, Tess can look at that region and try to see if there's an optical counterpart to it. All right, so at the very end, I will talk about exoplanet detection and characterization. And then, obviously, we can do questions I haven't gotten as many questions that I was expecting to, so I will just add to the time in which we do Q&A at the very end. Okay, so now about an exoplanet. So once you discover an exoplanet, there are a couple of questions you can ask about the characteristics of the exoplanet. The very first one is the very orbit of the exoplanet. Like, you can define an orbit in a three-dimensional space using just 6 parameters. So you can start measuring them, fine, okay, that gives you a dynamical handle on the characteristics of the system. But there's also the interaction with its host star, which you can study as well. And these tell you about the region in which the exoplanet is formed and how it interacts with the surroundings, both gravitationally and, if any, also friction-wise. Like some exoplanets are so close to their host star, there's actually some interaction between them. Okay, so coming back to searching for exoplanets in the test data, so there's a core team in the, that looks into the test data to alert all the astronomers around the planet about the possible existence of exoplanets. So this is a large pipeline in which many people actually work, including me. And what we basically do is we search through the resulting data validation reports of the incoming data and see especially what stars are more likely to contain or host exoplanets. Obviously, just looking at the test data, it is really hard to say for sure that there is or not an exoplanet. What we do is we assign probabilities, sometimes very much prior driven, sometimes very much data driven. But at the end of the day, the pipeline works as us alerting other astronomers, and then other astronomers, especially ground-based ones, going back, maybe collecting more data, maybe looking at archival data to try to figure out if there is actually an exoplanet. Usually the way you do this is you collect spectroscopic data on the same system. First, just to make sure that there's no binary star or anything like that. Or you can do high-resolution imaging, just look at the same patch of the sky, but with a much better angular resolution, better than Tess. So that will allow you to see if, for example, the signal is coming from elsewhere in the pixel or not. Things like that. But at the end of the day, if the candidate passes all these tests, then it becomes an exoplanet, a confirmed exoplanet, and then the idea is to measure its mass. For that, someone else has to collect a lot of spectroscopic data, and eventually, if the mass is also confirmed, or measured rather, then you know the radius from Tess, you know the mass from the spectroscopic data, so you can actually know the density, which is really cool. So that becomes the ultimate product. And at the very end, which I will come to, you can also study the atmosphere. But before I even come to that, I skipped one part. So there is a lot of data in the Tess, obviously, in the Tess data set. So it's a large data set. So the idea is not to spend human time just looking at every possible light curve, because there are millions of them. Instead, we have trained a convolutional neural net, which is a machine learning application, to do this, or at least do the first triage, that is, bring down the number from tens of thousands down to a few hundreds or maybe 1,000, so we can actually spend human time to look at them. So to do this triage, so it's essentially a really complicated convolutional neural net which does this for us, so we don't have to go through each and every candidate. Okay, so some highlights from the mission, especially the first few months. So I will obviously, Tess has discovered many such exoplanets, so I cannot enumerate even all of them. I will just show a few examples in which I spend a lot of my time just working on. So this is Tess object of interest 270. It's one of the, 3 of the exoplanets that we discovered using Tess. So here you see see the light curves associated with the system coming from 3 different sectors, sector 3, 4, and 5. So each of these sectors are 1 month long data periods. And on the x-axis, you have time. On the y-axis, you have the so-called relative flux. So you start counting photons from the system, and then you normalize it by the mean. That's what the relative means. It's nothing important. So the fact that you see these dips tells you that there is an exoplanet, and the fact that they're periodic increases obviously your degree of belief about the existence of such exoplanets. But without doing careful statistical analysis, it is really hard to just look at it by eye and say that these are exoplanets. But we've done basically all the necessary cross-checks and have seen that once you face-fold the data on the period, you actually get that transit-like or U-like shape that we always look after. So there's 3 such exoplanets with these periods. You can see that the planets C and D are in orbital resonance or near resonance. So that's something cool as well. Okay, so coming to the known exoplanets in the Tess data. So Tess obviously is a machine that can discover new exoplanets, but it is not a machine that only does new exoplanets. It can also recharacterize known exoplanets. So this is one example in which there's an exoplanet that rotates around or orbits around the host star, and a changing fraction of its surface is illuminated by the host star as it orbits around the host. So using this, you can start studying the so-called phase curve of the exoplanet, or rather the system. So star plus the exoplanet. So you start seeing these sine or cosine-like shapes on the light curve as a function of time. Well, this is actually phase curve, which means that you have found the period and then you have folded the light curve onto itself at that period. It is it is essentially a numerical method to study periodic time series. So once you do that, you start seeing these sine and cosine-like behavior, and that starts telling you about what, for example, what is the geometric albedo, if any, of the exoplanet is, and what is the temperature of the exoplanet, what is the day-night side temperature contrast of the exoplanet, or if, for example, there are tidal interactions between the star and the exoplanet, like because the exoplanet is there, sometimes it just happens that the star gets stretched along an axis and it becomes an ellipse as opposed to a circle. So you can start inferring things like that based on the phase curve. So this is a artistic description of what I was just talking about. So you have this giant star and you have an exoplanet, and because they're so close, we think that most of these so-called hot Jupiters are tidally locked. So you almost always see an example of this in the night sky. Our moon is like this. So our moon is tidally locked to our planet because of the same reason. And because it's tidally locked, it's one of its surfaces must be really, really hot, because imagine having no day or night, just staring at a star that is just going to touch you. It is really, really hot, almost as hot as the surface of the star. And they're really extreme systems, so we can start studying things like that using Tess data as well. Another thing is, I have been talking about the so-called period, the orbital period. I've mentioned it many times, but you may argue that there must be some perturbations to those periods. So it's nothing is perfectly linear, and you're very likely correct. In most systems, there are perturbations to this linear behavior in which the transit times happen to either get earlier or later with some pseudo period at very long time scales. So if you, for example, if you keep watching the period for about a month, you may start seeing that the period itself changes across the month. So this usually indicates that there is an additional body in the system. So there is like maybe a third body, and you can start discovering new exoplanets without even looking at them or taking a picture. That's also very cool. So that's another thing you can do using the test data. So this is just one highlight again from the mission, in which using the data on WASP-4b, which is an exoplanet in orbit around WASP-4. That's how we name exoplanets. We just stick a letter at the end. But we don't start from A. Don't ask me for why. So what happens here in this plot is, on the x-axis there's the time. On the y-axis, so there are two plots. On the y-axis you have the deviation from the linear model, this linear period that I was talking about. And this red point that we just observed using Tess indicated that the signal arrived much earlier than we expected. The Tess signal arrived earlier, which means that the period must have decayed, or there must have been some apsidal motion of the planet that we cannot currently understand or break this degeneracy. But we at least can start probing the two options. Another thing you can study is stellar flares. You probably know this idea from news, because we keep hearing that there's these space weather phenomena, and then people say sun is about to explode. Well, that actually happens regularly, and they are called sunspots or stellar flares. They're associated phenomena. And so they're very, I'd say they're very loosely associated, but the stellar flares are we think that they're a direct consequence of so-called magnetic reconnection events, because stars have magnetic behavior, we know, and sometimes these magnetic lines connect, and once they connect, they release a lot of energy, and the result is a stellar flare. And these three plots show how they reflect on the test data. So as a function of time, you see the the blue data points, and the blue data points suddenly increase and then start decreasing slowly, and suddenly increase and then start decreasing slowly again. Another example and another example. So we start detecting these using the test data as well. So there are many different pieces of physics you can do, actually. And I was just talking about the exoplanet atmosphere characterization as the very last step in this pipeline. So this is just a slide on that. So once you've discovered your exoplanet and measured its mass, what you can do is study its atmosphere, if there is one. Obviously, if you have an Earth-like planet, it's very interesting. Not all atmospheres are that interesting. Some atmospheres are just boring. There's just hydrogen, nothing special. But some of them have clouds. Some of them have really large scale height. This one doesn't. And some of them basically have Rayleigh scattering in them. So you start to characterize these based on the spectroscopic data that I was just mentioning. But just making sure this is not test data. You cannot do this with the test data. You have to have follow-up spectroscopic data from JWST, hopefully in the future. But currently, most of this data comes from HST. So here you see JWST, the James Webb Space Telescope, that is going to be launched into space sometime in the next decade, hopefully early next decade. And once it does so, we will get spectra like this, and just looking at the emission and absorption lines, we will know what type of ingredient there is in the atmosphere. And that is going to open up a new era for this type of analysis, where we will not just have a catalog of exoplanets, but we will have a catalog of exoplanet atmospheres. And that is going to allow us to do statistical analysis of the initial conditions of life, and how, like, basically that will become a science as opposed to just an area where we just hypothesize. So there will be a lot of empirical data to study there. So this is again Tess going back. I'll skip that. Okay, so now I just mentioned atmospheres, so that probably naturally brings the discussion to searching for life, because once you start characterizing atmospheres, the very first question you ask is there life? Or first of all, is this atmosphere that I just observed suitable for life? And the second question, is there actually life? They're actually separate questions. But one thing I have to mention even before discussing that is that we should probably think about our own solar system before even going further out into exoplanets, because there are many, not just planets, but moons to our planets that are in our solar system around Saturn and Jupiter, like these four. These are interesting. Well, excluding Titan itself, it's also interesting on its own, but these three guys probably have a subsurface ocean, and that makes them very interesting because eventually we may be able to send a probe down and probe from that ocean. And if that ocean ever comes into contact with a hydrothermal vent, then we are in the game, because you may actually have a rich set of hydrocarbons that may initiate life. So these three might be optimal, or at least have the capability of being optimal for producing life. And Titan also is interesting because it's got lakes on it as well. But that's so it's got a really thick atmosphere as opposed to these three. The atmosphere of these three aren't really interesting, except the fact that they allow us to sample from the subsurface ocean, because there are so-called cryogeysers where some material from the subsurface ocean is ejected into the outer space, and if you actually run like a spacecraft past that flume, then that you can sample them and study them without even going into the ocean. So that's a cool. Oh yeah, here's the cryogeysers that I was just talking about. Yes, please.
Are there any necessary and sufficient conditions for life existence of life on a planet? For example, if you want to say that life, for example, a planet can sustain life, it should have these conditions, for example, for necessary conditions.
Well, unfortunately, we don't. If we knew, this would have been exponentially easier. So currently, we don't have any observational evidence to support any of the models. The problem is there are so many models, there's so many ideas, but nothing to start eliminating them. Once we have a good sample of atmospheres, we may be able to start addressing them and just start eliminating models. So we can start to look for common features of these models, and then they'll tell us about something that, like, if there's a universal prescription for producing life, that will be the common denominator of those models that survive this experimental test. Yes, please.
What about using Earth as one of the models?
What about using what?
Earth as one of the models.
Well, sure. I mean, Earth is the only sample we have. That's the obvious case. But the problem is just you have a single data point and an n-dimensional parameter space where n is large, and I really mean large. So you really can't constrain anything. So, okay. So, okay, that's a good statement to move on with. Where's everybody? So I just stated that the Earth is the only example, and that is unfortunately true. For those of you who believe in UFOs, I'm sorry, but we actually don't talk to them, or we don't actually have any evidence for the existence of extraterrestrial intelligence at the moment. So the natural questions, the natural question to ask is, where is everybody? So we think that there is about an exoplanet on average in our galaxy per star, or I should say per sun-like star. That ends up because there are about 400 billion stars in our galaxy, that ends up being a number like 400 billion exoplanets just in our galaxy, leaving alone all the other galaxies whose number is also in the hundreds of billions. So there must be such a huge number of such initial conditions. So even if it is really, really unlikely, one of them at least must have produced life other than ours, and they must have come to the stage where they're able to talk to us. But the very fact that they don't should tell us something. Something in our understanding must be wrong for this to not be the case. So there are many ways in which you can start explaining this. I will talk about one thing, but probably even before going to that, I should just mention one signal that we observed. This is almost a half a century ago, actually. It's been a long time. This is called the Vowel Signal, in which radio astronomers were listening to basically a patch of sky, and then this is in logarithmic scale as a function of time, the amplitude of the signal they observe, and suddenly, if you just run down the numbers like this, you suddenly start seeing a really large numbers, and then the technician there just wrote wow, because he or she was really excited about seeing these numbers. But this signal that was observed almost a half a century ago has never repeated. Many people from very different institutions have looked at the same objects again and again and again, and have never been able to reproduce the same result. So people think that this is just some emission reflecting off of space junk. That is an unfortunate thing, that we have a lot of junk in space. So that is very likely that this was just a reflection from space, or an instrumental effect, but it's really unlikely that it's instrumental, because it's very coherent. So people don't know, but it's very unlikely that it's actually extraterrestrial intelligence. So there is another side to this discussion, which is active SETI. So SETI, by the way, is search for extraterrestrial intelligence. People have been doing this for almost, well, more than a half a century, actually. At the moment, taxpayer money, usually like using taxpayer money to do SETI is a thing that's frowned upon, especially in the US, because people think that we should just be doing astrophysics and trying to understand the nature, as opposed to looking for extraterrestrial intelligence using taxpayer money. But there are many private institutions who fund such studies, and also active active searches for extraterrestrial intelligence. This is just one example, but a very symbolic one. Sorry?
This is the Arecibo message?
Yes, this is the Arecibo message. So the way to read this message is you start from here and then go like this. And so if you were the guy who's receiving this, you obviously don't receive an image like this. What you receive is a sequence of ones and zeros. So you start from here and then just go like this, receiving zeros and ones. And because the sides are both prime numbers, it is just expected that the receiver on the other side is intelligent enough to know prime numbers and then bring this into a picture-like form. And once they do so, they must recognize that this is not random noise, because if you choose any other side length, it just looks like noise. But once you choose this configuration, it just becomes an image. So using this, so this is just numbers like 1, 2, 3, etc. And then they have an image of the human. That's kind of funny. They have, I think these were like carbon atoms somehow. They're like the organic molecules that were known at the time. They were thinking that they kind of represent life. So they sent out a message like this. This is a pictorial schematic description of the Arecibo. Arecibo, by the way, is a transceiver. It's in Puerto Rico. So it's been one of the prime sites in which active searches have been done. Okay, so with this, I've spent about 45 minutes, and I will shut up, start collecting questions. So I'll just finish off saying that exoplanets are definitely fun. So if you have further questions, I can definitely answer now or after the discussion session. And what I really like about exoplanets is that they put us in cosmological perspective. So I think in that sense, it is very distinct from the rest of astrophysics and probably have a lot of common denominator with cosmology itself, because they really put us in a position to look back into our own past and start questioning stuff. And coming back to Tess has a really rich data set. It's been in space for about a year now, past a year almost. And it will hopefully be in space for some time to come. There will be an extended mission, hopefully. And that extended mission will continue for about 3 years. And then it is likely, if nothing breaks, it is likely that there will be yet another extended mission. So NASA's policy is usually that if nothing breaks in the instrument, they usually like to keep it in space, because keeping it in space is much cheaper than sending another one into space. Okay, with that, I'll just conclude and get questions. Thanks for listening. Yes.
So do you have some comments on that? And second thing is that, what about after the detection? What is the next steps for this? Because NASA is also funding another W-FIRST mission. So is there any possibility to cross-correlate the data set between two of these experiments?
Yes. So for microlensing, that is certainly true. I've only mentioned 2 indirect methods. There are actually even more than 3, including microlensing. There's astrometric as well, and there's pulsar timing, etc. So there are like many ways in which you can look for these things. However, the other methods that you and I mentioned, the problem with them is that they are not statistically complete. Well, none of them actually is statistically complete. All detection methods have selection bias that is inherent. However, some of them have more selection bias than others. However, at the end of the day, I think we should be trying all of them because of the different selection biases. They sample from the different regions of the underlying population of exoplanets. So it is important to have all of them. Now, your question about WFIRST. So WFIRST is a really nice experiment, and I think almost all astrophysicists would agree that it must actually fly. However, very recently, the funding for WFIRST, I think, has been impeded by many things happening. And the primary problem is that US started to say that they want to go to moon, and that eats a lot of money from WFIRST's budget. So when you hear news that Trump wants to go to the moon, what happens actually is most of the astrophysics money actually is directly sent into the robotic, or actually not even robotic, like human space flight. So unfortunately, WFIRST may or may not fly, or at least may fly, but fly very late, maybe like in the later chunk of 2020s, if it does so. So that means for a long time to come, we will not have such a cross-check, unless something else gets funded real quick, or Europeans just find a way. Yes, please.
So just a technical question. What is the cadence with which Tess observes a single star?
So there are 2 modes.
Is that a continuous 4-hour window that you were showing in the plots?
So there are 2 modes of cadence. One is the short cadence, which is 2 minutes. The other is 30-minute cadence. The difference is that 2-minute cadence data is collected only over a subset of pixels that are pre-selected to be around stars that are of interest to Tess. So there's a list that is called the candidate target list that contains about 200 stars per mission. And the pixels around those stars are collected at 2-minute cadence, and the rest of the silicon is collected at 30-minute cadence. Another thing I should add is the shutter time of Tess is actually just 2 seconds. So the addition from 2 seconds to 2 minutes is done softwise. So it's basically done on board.
And then you're focused on a star continuously for how long?
For about a month. So what happens is the one orbit is about 13.7 days. So Tess stares at the same patch of sky, or at least tries to stare at the same patch of sky. Sometimes there's systematics that change the pointing accuracy of the instrument. But anyways, so 13.7 days it collects the data, turns back to the Earth during perigee, sends back the data, and then in the second orbit just looks at the same patch of the sky. So then it collects 2 orbits, which makes up a sector, which is about a month long. But I've been saying month, but it's actually not 30 days. It's shorter.
And then after that, you never go back again?
So far,
Time in the far future.
yeah. So in the nominal mission, we don't, but in the extended mission, we will. So the idea about the extended mission is to look for exoplanets that have much larger periods, because a month is not enough to just find exoplanets whose period is 60 or maybe 90 days. However, if you just look at the same patch of sky for 1 more month, about 2 years later, then you may, statistically speaking, start finding exoplanets that may have periods of about a year or even longer.
What's the sensitivity of Tess in terms of the size of the star and size of the planet? Let's say, can Tess observe a planet that's 400 parsecs away, that's 1/10 the size of the star?
Yeah. So this is a question that very much depends on the brightness of the star. So there's essentially a curve as a function of the brightness of the star, a curve that characterizes the photometric uncertainty, the noise, and a couple of numbers of interest. If you have a magnitude 10th star, the photometric precision is about 200 ppm, parts per million. If you have a 16th magnitude star, the sigma, the 1 sigma fluctuation is about 1%. So if you have 1% photometric uncertainty, then you essentially can only do better you can only start looking for signals larger than that. And also, given the fact that it goes like the radius square, you start really looking for really large exoplanets. Otherwise, you can't see it. Like that usually happens with white dwarfs. They're really faint, so you really need large exoplanets. But white dwarfs are small as well, so you gain. Yes?
You said it can also check out some optical counterparts of gravitational waves.
Yes.
So will it leave its current mission and turn to the...
No, it doesn't do that. So the TESS is a survey mission, which means that you cannot disturb the sector schedule. So this counterpart argument I was making is only by chance. If it just happens that to be in the TESS data, then we can actually do that. Yes.
So for that equation, it's like some function coefficients with some different parameters, something like this, and which actually tries to somehow find the, let's say, correctable way of finding some other, let's say, aliens or life, any other things all over the universe. So is there any way to check out that equation, or maybe check some of the function coefficients of the equation, like to change them maybe another functions which can mean anything different? I want to say, like you said that you are seeing some different exoplanets and try to understand if there is anything alive in it or not. Maybe any other coefficient, like any other coefficient function, can be more meaningful in terms of the equation. Can change something?
Well, you certainly can. I think the problem is, like, you can certainly take the equation and then start reparameterizing each factor in terms of other things, which at the very end make up the same factor. That's certainly possible. The problem, I think, is even if you do that, there are many versions of that equation that tries to do that. I think at the end of the day, they're again prior driven, in the sense that the famous, like the zeroth order question, the equation has the initial terms as the star formation rate, the number of planets per star, and the number of Earth-like planets per per planet. So those three terms you can statistically answer using missions like Kepler and Tess. So leaving those three aside, the rest, which is the fraction of planets in which there's life, the fraction of planets which can produce life, then fraction of life that can produce technology, the fraction of civilizations with technology that choose to communicate, etc. Those ones are largely prior driven, and even if you reparameterize, I think they'll still be prior driven. Like that part, I don't think we have any hope of doing any science with, because they are not things that you can count or put uncertainties, like statistical uncertainties, on, unless you start making a population of, let's say, life forms that have produced technology or not. Like if you have, let's say, found 100 exoplanets with the right biomarkers saying that they have or not life forms on them, you can start answering the question, what is the fraction of them that actually ends up with technology? But then if you are at that stage, you don't need that equation anymore. So it's like solving the equation while trying to answer this question. So we don't have really hope, I think, but I hope someone else proves me wrong. Yes?
Thank you for the talk. Could you give a little bit more detail about the sensors on the equipment, such as like the pixel size, the array size, and the noise floor, and what you use for sensors in one camera? That's okay.
Okay, so the photometric noise, the noise floor, I think mentioned. So the noise floor past 10th magnitude is about, so pre-flight, I think it was expected to be about 60 parts per million. Now we're down to about 30 or 20 roughly for really, really bright stars, 20 ppm. Other than that, the silicon essentially has 2048 pixels by 2048 pixels. And there's virtual columns on both sides, and that columns as well. What other questions did you have?
How do you handle the one-way noise for such long-term measurements? Like you're looking at the same stuff for like a month.
So what we do is we do so-called detrending to get rid of the red noise. So red noise, by the way, is structure in the data that you cannot model using your forward model exoplanet. And what we do is we do Gaussian process to filter out the trends. There are many trends in the light curve that are due to other things, like the pointing accuracy just shifting, etc. or for example, in the beginning of every orbit, just because Tess has moved, its thermal state changes because it basically points away from the sun and into the sun. And then because of that, for about a day, the temperature of the machine changes. So we usually just even mask out that part, because when the temperature changes, PSF, the point spread function, changes, which means that the photons from a given source is spread out into a changing fraction of the pixel. That is not something you want, because it introduces trends into your light curve. But anyway, so most of these things can be just like even gotten rid of just using Gaussian processes. The nice thing about looking for exoplanets is the signature is so unique that is usually not covariant with anything like 1/f noise. Yes?
Is it dominated by the thermal noise of the CCD, or is it dominated by the radiation space? That is the positive.
So again, it depends on what magnitude you're interested in. So at very faint magnitudes, we're always, like any optical telescope, is always background dependent, like sky dependent. The 1 sigma fluctuations in the sky will determine what magnitude you can probe. In the bright limits, you're always systematics dominated, because there's a floor. Even if you observe a brighter star, just because your readout noise will scale with the number of photons you collect, there will be a floor of the noise floor. So in between the two, you're Poisson limited. So basically, there's the Poisson process. You count photons from the star, and that basically is the major source of error.
Did you just survey our galaxy or not? Since if we want to see an object far away, like how about we have to fix on an angle for a long time to collect the photons? So it seems not fixed on an angle for a long time now.
Can you repeat?
The distance will be very short.
Can you repeat the question?
I mean, did you just survey our galaxy or outside of our galaxy?
So we survey about 90% of the sky. We exclude the ecliptic plane just for the nominal mission. In the extended mission, it will be different.
But if you want to see an object which is far, you have to fix on the angle for time enough.
Yeah, that's about a month. Obviously, there's like a limit to the photometric noise limit. So I'm not claiming that Tess is a very deep mission. Tess is a very shallow mission. So, for example, the catalog that Tess produces is not complete when you compare to things like Gaia or Hubble Space Telescope, because Tess spends minimal time just looking at a patch of sky. And if it spent more time looking at the same patch of sky, it would probably not do better, just because there's a finite pointing accuracy. So, like, even if you try to look at the same point, what the telescope does is it basically starts moving around that point, and then your photons get scattered all around.
Did you say the equilibrium point or just?
No. This is Earth or Earth orbit. Yeah.
How many kiloparsecs?
Sorry?
You said it's a shallow mission.
Well, so the kiloparsec totally depends on the luminosity of the star in question. So when we quote completeness, we cannot quote basically a distance. We can only quote a magnitude.
For a sun-like star, how far?
For a sun-like star, I think I don't have the number off the top of my head. The problem is Tess never tries to be complete. And the reason is we almost always, we never add up images. And because that's not very useful, because Tess is not designed to do that, we only look for temporal variations. Yes, please.
Have you already stared at Cygnus region where Kepler was basically observing?
No, that's going to happen in July. Yeah, that's very soon.
So if